our lecture series. This is the last lecture on structural dynamics. And today we are just going to have a continuation of what we've been doing last week. And we start with, sorry, I was monitoring my audio there. It's okay. So if you have any query, there is a chat section there. If you can hear me well, it's good always to confirm so that I know that we are together. And last week we looked at free vibration. It's kind of the second lecture was when we started the calculation. The first lecture was just an introduction, bit of it, the theory, the definitions. But today we look at the second part from last week. And we talk of the free damped vibration. So remember the equation. Let me just make this full screen, right? So we talked of the equation of motion, or the fundamental equation of motion. This is the same, or it's standard for all cases. So you say that mu plus ku, or ma, or mu double dot. This is the acceleration times c velocity plus ku is equals to ft. This is the external excitation. And we started with the cases whereby the external excitation is 0, so that now we can be talking of free vibration, the vibration that occur just because of the initial condition. Maybe you just cause a displacement and then you allow the motion to continue. Remember, for the vibration to occur, I mean, for us to study structural dynamics, we talked of the reciprocatory motion. Otherwise, if it's just when you push, you release, it comes to a standstill, then we will not have a dynamic system or dynamic analysis, a motion to analyze. Okay. Now, thank you, Michael Wesley. You saying you can hear me well. Thank you. I can see people are logging in. 37. We should go higher. Number should be over 100. And today is a short lecture, so at least try to be apt so that you are not left behind. So it's kind of, we're going to analyze different cases. So we have to hold some part constant so that we can start from basics, from a simple model, a simple equation. Then we continue building our concepts. And in this case, we said, let's first of all hold the external excitation to be 0 so that we talk of free vibration. We are going to see when there is forced vibration. And then we limited ourselves first to single degree of freedom case. Yeah, we're going to see cases now when we have multiple degrees of freedom for multi-story building. Now, in this case, last lecture number 2, we talked of when there is no damping. So this component, C times velocity, was equals to 0. So our equation becomes very simple. It was second order homogeneous linear differential equation. So it was easy to solve. Now today we look at a case when the damping is there. Okay, and this is a typical for real life scenarios. So we are moving from an ideal case, yeah, and in an imagined case, to what is expected in real life situation. Remember, even real life free vibration, yeah, it may occur, but there is always be damping because, of course, the environment, there is the fluid flow of the air. Okay, but we will not have started with those complex cases because our equation, the hard calculation have become tedious. So we need to build our concept step by step. So today we are going another step. Damping is there. So we introduce back the component C. C is a damping coefficient times the velocity. And remember, we confined ourselves to viscously damped structures. That's therefore the force is directly proportional to velocity. And from that, this is why this component, we are able to derive or to incorporate this component. Now, in this case, when we introduce this, you see, this is a second order ODE, right? Remember, U double dot here, we are just using the double upper dots to simplify our expression. But this is d squared U of dt squared. We do not want to keep writing all this. So you find in many books, there's a simplification, right? So in that case, so this is a second order homogeneous, the second order ordinary differential equation, but it's not homogeneous. Okay. And we know from ODE, I know by now you have refreshed your ODE, ordinary differential equation course. We know that the trial solution for this is of this form. C which is a constant, an exponent raised to lambda t. So this is just refreshing what you studied. When you talked of the characteristic equation, we talked of the lambdas, you know, all those coefficients of damping. We are now using them in practical cases here for our analysis, our understanding. Okay. Now, in this case, we already now have what is the trial solution. So what we need to do to get the typical or the trial solution is of this form. So what we need to do to get what is our response? Our response, remember, is displacement. We want to get like this equation. If this was x, this would be x d squared d over d squared x over dt squared, like that. So in this case, displacement, we are using u. So it's like we want to find what is u. What is the displacement? And we know our displacement will not be one constant value. We can have a displacement at a certain time. But because of this dynamic motion, it's a dynamic analysis, there will be the to and from motion, vibration. So it means we can only express u as a function. And how our structure will be deforming, we call it a response. So at times you may find like now we are not just talking about what is the displacement. We'll be talking about the response. The response could be displacement, could be the internal forces, but in our case here, our equation, the value of the unknown u, which is the displacement, we'll be talking of the response of our structure. So that now we will have it in form of a wave or a function. Okay. Now, so this is just a typical value at the endpoint. U is equals to e raised to power lambda t. So what we need to do, we substitute this in our equation 24. To do so, you differentiate twice to get the acceleration and once to get the velocity, then you substitute back. And what you'll find is that you have a common factor because, of course, when you differentiate these ones, u ones, you are going to get lambda c e raised to power lambda t. When you differentiate again, so this is a u dot there. Then if you differentiate again to get the acceleration, u double dot, you have, again, you differentiate this, you have lambda squared c e raised to power lambda t. And then you substitute them to equation 24. So you're saying for all these, c e lambda t is common, you know, either in acceleration, in velocity, or in displacement. Therefore, we can cancel those common factors out. You'll be left with m lambda squared plus c lambda plus k is equals to 0. And this is what you call the characteristic equation. Yeah, you see, just a refresh. So class rep, what is happening? Where are the other people? They lost their way. Yeah. So make sure that you don't just record the class attendance there and then you go to your work, because it always reflects with the when you come to marking. And yesterday we had the meeting for the exams, and it's pathetic. It's good, but just study. Don't plan to copy. Just study. Oh, you are not telling me I'm on video. Sorry. I should put this off so that to avoid distractions. All right. So to solve this characteristic equation, of course, this is a quadratic equation. And what we just need to do is use the equation. You know, of course, x is equals to plus or minus b squared over 2. Is it minus b plus or minus the square root of b squared minus 4 is c over 2a. This is just the equation that we are using to solve nowadays here. And therefore, because this is a quadratic equation, we know that we shall have two roots. So one, when this symbol is, or when the sign is positive and when it's negative. So by doing so, you're going to have that lambda, you have lambda 1 and lambda 2, okay? And in our solution now, the equation 25, we are saying the general solution will be the superposition of the two, you know, when lambda is 1 and when lambda is 2. And this is why we are giving the general solution. C1 and C2, of course, these are constants, and they are predetermined from the initial condition. Okay. So now we have obtained our equation. We have our equation of motion. We have our general solution. So we need to get what are these constants, of course, so that now we can see how our response is. So first thing first, we need to define a few things or a few important terms here. In this equation, or in this expression that we are having here, you can have a case when all these constant, all these components under the root sign is equals to either positive, negative, or 0. For instance, when this C over 2m squared is equals to K over m, then it means all these collapses to equals to 0. You can have a case when this first part is greater or is less than this second part. Therefore, whatever will be under the root is will be negative. Again, if this is greater than this part, whatever is under the root will be positive. Okay? So this is what we are defining here. Based on the sign under the radical or under the root in equation 27, of course, it can either be 0. We talked of a critically damped system. It can be positive, that will be an overdamped system. It can be negative, that's an underdamped system. Let's see what we are saying. We are saying whatever is under the radical, this part, if it's equals to 0, if it's equals to 0, that's a critically damped system. So we are saying all this is equals to 0. And for this to happen, it means, look at this equation. We have C, equation 27. C, this is the damping coefficient. So the damping coefficient, it means, remember the damping coefficient is that attribute that tries to bring our motion to a stop or to a standstill. Okay? So you are trying to stop our motion. Now, if that there is, let's say for our motion to continue, of course, in real life, we are saying damping will always be there. But if damping is small, if the damping factor is small or coefficient is small, our motion will continue for a long time. If that damping coefficient continue increasing, right, our motion, maybe vibratory motion, will be just for a short time and then it comes to a stop. Now, if it exceeds, it will come to a point whereby that damping value exceeds a certain value, such that now there is no more oscillation or vibratory motion. So it means for vibration to occur, the damping value has to be below a certain critical value. And that's what we are defining here in this, that for critically damped systems, it means the damping value have exceeded a certain critical or is equal to a certain critical value, just equal to. And therefore, that's why we are saying the root under the radical or the component under the radical under the square root equals to 0. And in this case, it means we are just at that point where our vibratory motion can be stopped. Okay, let me combine with the overdamped system. The overdamped system now will be the damping coefficient have exceeded that critical damping value. Therefore, we have stopped any vibration or vibratory motion. So even at this stage, before we go to the other damped, you can see the disclaimer I put here that no oscillation will occur for cases A and B. And for our case, because we are in dynamics and we want to analyze vibration, it means for cases where there is no vibratory motion occurring, then no need to consider further. Okay, and that's why we are dropping cases A and B. For critically damped system, it means if it was free vibration, which is critically damped, we just cause an initial displacement. So we have just initiated, we said, let's say this is our structure. Okay. This is our structure. Then we initiate or we introduce an initial displacement. Okay. So there was an initial displacement there. And we say this is the U naught, if it's a certain value there. So that what displacement we release. So our motion, we expected our motion to occur to and fro. But if it's critically damped, it means this structure will just come to rest there and stop. Okay. If it's overdamped, you might even realize that there is no motion at all, even when we displace it. But let's not dwell so much on this, so that you can we first introduce the third concept or for that type of damped system, so that now you can see, you can appreciate why we are saying for these two cases, there's no need to consider them further. But some expression here are of good concern because we have known C critical. We have introduced a new notation, C critical. Okay, and from this expression, we are saying C is equal to C critical for critical damped system when the root at the when the values at this root is equal to 0. So from here we can have an expression, or we can derive an expression for C critical or critical damping coefficient. And we are also employing. Remember, we derived what is the angular frequency. Just equals to the root of K over M. So we are utilizing that. That was equation 11 in your notes. And to simplify this expression 29. So we are saying C critical or critical damping coefficient can be expressed either in this form or in this form or in this form. Okay. So this is a good expression that we shall use it later on. Now let's move to the how this happened, or to visualize what this kind of motion is all about. So remember, for an undamped system, if it was an undamped system, we do something like this. And maybe let me just draw something small so that you can see it here. We do something, okay, maybe that will confuse you. Let me just continue from here. So we do something like that. Okay. This is undamped. The amplitude, if this was amplitude U1, is the same as U2. Now, for a damped system, the motion continued dying out. It means the amplitude U1 will be greater than U2, continue decreasing like that. Okay. Now, for this critically damped system, actually, there will be no oscillation. So you can see there will be no up and down motion. It's just, we started with an initial displacement, and all of a sudden it just comes to a rest. And based on the value of the damping or the damping ratio, and these signs we need to change. We had used the eta, but later on I realized we need to use this symbol. We call it xi. Okay, so later on in the next slide, you are going to see this symbol changes. This is just eta. So, but whatever we are saying is that we are talking of this being a C of a C critical. Okay, for critical damping, we are saying C eta is equals to 1 because C is equals to C critical. And that's why we are saying for overdamped system, the value continue with increasing. The damping value is far much greater than the critical damping value. So you can see our motion just is like a straight line there. There's no oscillatory motion. You cannot see a wave or a kind of a wave. Okay. Now, this was just to express or to tell you when we have critically damped system, there will be no oscillatory motion. The motion just dies out exponentially. Okay. Now, let's move to other damped system. Now, at a damped system, this is a motion which is oscillatory, and this is the motion that is interesting to us because we want to have a motion we can analyze to and fro, to and fro, to and fro like that. Okay, because we are talking of, we are not in static analysis. If we just displaced and then the motion came to a standstill, maybe the dynamic analysis is no longer of interest. Maybe that structure can just be analyzed as a static, using the approach of static analysis. So, but for us, we are looking at where there will be oscillatory motion. So for the damped system, C is less than C critical. That is the damping coefficient. The actual damping coefficient is less than the critical value. Remember, the critical value is at the point whereby now, or after that, or from that point, if the value of damping coefficient exceeds that, there will be no oscillatory motion. So for us to have oscillatory motion, we are saying, let's maintain our damping coefficient below the critical value. Okay. And for that to happen, it means something here. It means that I'm going back to the initial equation 27, and it means the value here, the value under the root will be negative. Okay. And for this now to, this will be negative. Now, if you look at the equation, the one that you're going to see later on, we have rearranged K over M. K of m has become ahead because what we are doing here, for us to be able to get the square root here, we have multiplied with the -1. Okay, so that we can get what is the square root of -1, -1, which is equals to I. And then if you multiply each one of these -1, this becomes negative, this becomes positive. That's why it's rearranged in the other case. So you'll have this as K over M minus C over 2M squared. Okay. And then we are going to introduce the I because we have obtained the square root of -1. I was doing it that here so that when we come to this, to the expression here, you are not surprised why now our equation has gotten an I here and why now this one have interchanged. Okay, it's because we know that whatever is under the square root, we wanted to remove that negative from under the root, and we utilized the principle, the identity that the root of -1 is equals to I. Okay, so you see now we have complex numbers here. Good. Now this we are still trying to obtain the response or the value of U. You know, remember we obtained the trial solution U. We obtained the general solution U after we have gotten the root for this characteristic equation, the lambdas 1 and 2. So we needed to get now what is C1 and C2. And that to obtain that, we wanted to know about the different types of vibration that can occur. Then we have rearranged this equation 27. So we continue. We continue now from this part. To do so, we want to handle the I, the negative, the complex number. And we are utilizing the Euler's equation. I remember even last week, we utilized this. And I believe maybe it could be in your SMP. How you can, the relationship between the sine and cosine function is a trigonometric function with the complex relation that we are utilizing. And we utilize this. And then we substitute equation, you see equation 31 into equation 28, because already now these are the lambdas, and the equation 28 is our solution. Equation 28 is our solution. So we are substituting the lambda 1 and lambda 2. And at the same time, we are utilizing this Euler's function, Euler's equation, so that we eliminate the negative, or I mean the complex number, by utilizing the exponent. Okay, so there is some calculation here. I just summarized. It's condensed. It's condensed. So I'm just giving you the add product here, the equation 32. This is at the time that we have already obtained what is, we have already substituted this equation. We have already substituted for lambda 1, lambda 2, and we have used the Euler's expression. I hope I'm not flipping to and fro too much. I don't want people to get lost. But the good thing is that you have the note. So you are moving together. So this is our general expression, equation 32, for our motion. And of course, we have the constant A and B. And we are talking of A and B being redefined constants. Now, redefined constant is like, remember in the first case, we had A, C1 and C2 as we had C1 and C2 as the constants. So a constant is a constant. I can come and say here, if I'm talking about constant, if I say you have C1, I have C2, I can add them here and I can call them C, because still a constant. So whatever we are saying is that this A is not C. It could be C plus C1 plus C2. So these are just other redefined constants. The thing about constant is that they are not varying. Okay. So they are redefined constant of integration. And then now the omega, which is the frequency, we introduce subscript D to imply the damping coefficient. Okay? So to imply that this is damped motion. So this is about the damping frequency of the system. Now, what is remaining? We need to get exactly what are these coefficients of integration. Remember, whatever we did here, we were not getting what was C1 and C2 that was in the previous equation. We are just substituting the values of lambda 1 and lambda 2, and now we utilize the Euler's equation to get rid of the complex number, so that now we have this expression. And our expression, we have still the constant have not been determined. So we need to go ahead and determine this constant. So the equation here, the damping frequency, we have called is omega d. This is given by the square root of k of m. So this component here, is the one that we are referring to as omega d. Okay. The root of all that is omega d, and it's given here. And now utilizing equation 11, if you go to your note, equation 11 is the omega, the undamped. This is the root of k over m. Okay, so we are utilizing that. And again, damping ratio. This is where I was saying the sign that I had used before. I had used eta, but now we are using xi. All right. So the damping ratio is equal to the damping coefficient of the critical damping coefficient, CCR, C critical. Okay. So utilizing this and this expression, you can simplify equation 33 to have equation 34. Omega d is equal to the undamped angular frequency and the root of 1 minus xi squared, or damping ratio squared. So this is just a matter of simplifying how we can express. You know, now we are seeing the damping frequency is a factor, or it's a function of the undamped frequency and the damping ratio. All right. Now, the constants of integration, the one that are in equation 32, we are saying they can be, of course, this constant of integration can be obtained from known initial condition. Remember, I refresh again your memory that in finite element analysis, because we are getting the constant, we are using the boundary conditions, we are talking of solving a boundary value problem. In this vibration, we are using initial conditions to know the value, to determine the value of the unknowns, the constant. We are talking of solving an initial value problem, IVP, right? And that one I believe you've covered much in mathematics, either in calculus, numerical analysis maybe, or ODE and PDE. Okay. So what are the known initial conditions? We know at time t is equal to 0 because this is free vibration. Then the initial displacement, if we apply a certain initial displacement, we can have u is equal to u naught. And if we release it, you can say the initial velocity u prime is equal to v naught, or the initial velocity is equal to v naught. So you can substitute this in the equation that 2. The 2 is the equation with our, this was A, and then we have the B there. So you substitute these unknown values, and then you solve equation 32. We are solving this equation 32. You have substituted the values of when at the initial, when u is equal to u naught, you substitute that, you obtain the value of A, and then you use when v, you differentiate once, you get v naught. You're talking of differentiating this equation to get the velocity, because you know v naught, when a time is equals to t is equals to 0, you are going to get what is b. And with that, we are able to obtain the constant of integration a and b, or in simplified form, you get equation 37. And how did we simplify this? Remember the identity, trigonometric identity, cos A minus B. This is equals to cos A, cos B, plus sin A, sin B. So here, because we didn't have, you know, cos A, you can say this is the A, and this is the A. So the B is the alpha that is introduced here, okay? And then we have the compact format here. So we are simplifying our equation further. So you see the mathematics you learned back in geometry, back in calculus, we are using them here to simplify our workings. Okay. Let me know if you can still follow me, if you're still together, if you are lost somewhere. I know it might seem overwhelming deriving this, but I've tried to simplify. So there are some steps that I've just jumped. But if you are to derive this, let's say in an examination scenario, we need to see the step. We need to see the substitution. We need to see you substituting this in equation 32 for the displacement. And then we need to see you differentiating equation 32 and then substituting V naught at time t is equal to 0. We need to see the workings. But at this stage, I felt that it's good to just not overwhelm me with that. And where C, of course. Now, you see, we had this equation 36. We had it in a complex, we had it in an expanded form, but now we have it at 7 in a compact form. And now the constant C is in compact form given in equation 38. And now tan alpha is defined as given by the expression 39. And we are trying to now analyze or understand what kind of a motion are we talking about here. So when U naught, when U at time 0 is equal to U naught and V at time 0 is equal to V naught, and this damped vibration, this is the kind of motion we are talking about. We start with the initial displacement U naught and initial velocity V naught, but V naught here is equal to 0. Remember, the velocity, if we are starting like this, you always find like the velocity is defined as this, the tangent here. This will be the V naught. Because the velocity, of course, is the gradient of the displacement. Okay. So in this case, now we are saying, if the velocity, initial velocity is equal to 0, it means, so we are starting at horizontal. There is no initial velocity 0, and then our motion declines like that. Now, as you can see, we said because of the damping, our motion continue dying out, such that the initial amplitude, U naught, U1 will be less than U naught, U2 will be less than U1. The motion continue dies out because of damping until when there is no vibratory motion, our system comes to rest. But at least because it was at a damped system, we had some oscillation, and it's also periodic. Now, the equation in the other graphs that we are showing for critically damped, we didn't have this bottom part here. There was no, oscillatory means it's repetitive, going to and fro, to and fro. So in this case, for the damped, now you can see the to and fro motion can be seen because we are seeing the motion coming down, up again, down, up again. But for critically damped and overdamped, it was just coming to the rest. There was no vibration or reciprocatory motion. Reciprocating is like repeating to and fro. So this one is oscillatory and periodic. And we can see, of course, amplitude decreases with time. And the damped period, of course, remember the period was given by, which is, of course, period is 1 over f, was given by 2 pi over omega. So in this case, because we're talking of damped system, so damped period will be the same equation. And we knew the expression of damped frequency, utilizing the undamped frequency and the damping ratio. So don't confuse between the term damping ratio and damping coefficient. Coefficient C, ratio is xi. Now we have found the constant C, and we have seen the solution to our motion. So it's kind of, we have obtained the response. So at any one time, we can come and say, for this system that is damped like this, with this damping coefficient, we can say at time t is equal to 2 seconds or 3 seconds, we can just come and obtain here what is the displacement. Now, as you can see, we can have, there is this dashed line. It's just showing the general decline in our amplitude. Okay, the amplitude continue declining. And as you can see, it's declining exponentially because of this part. And this is the same, you can see it from this equation. The exponential decay. The exponential decay that is here. This is this part. This is the exponential decay part. This is the vibratory part. Okay? Of course, with damping. This shows how our amplitude is declining. We want to introduce another concept. That's why we are mentioning about that. And of course, this is when we have the maximum amplitude. And we know the maximum amplitude is when the cos is equals to 1, or the component here is equals to 1. Therefore, now with our motion, with the same, for you to understand between the free, they are damped and damped, we are just sketching here for your understanding that for undamped, it means the damping ratio is equals to 0. There's no damping, right? So this is the motion, the continuous line is the motion. So you see the amplitude is the same. So this motion, if it's free and damped, it continues forever, indefinitely. So as the damping ratio increases, you can see from B, C, D. D is a short continuous dashes. This is the D. Sorry, the D is this one. If the damping ratio is very continue increasing, this is 0.5, our motion will die out quickly. So we are showing the effect of damping and the different damping ratio to our motion. So this is the system that is shown. So we are just having a mass of 10 kilograms suspended using a spring, and there is a damping. So maybe this damping could occur as a result of, because we are talking of the viscous damping, the inherent characteristic of the material. So the friction between the material of the spring, maybe apart from the stiffness, could bring about the damping. So that's why we are saying after some time, this motion moves to and fro, and then comes to a standstill. And the displacement, which is the amplitude, will be based on how much the damping ratio is. Okay, good. So let's see how we can estimate damping in a structure. Because we are talking of, we always, for my case, I usually try to limit myself to a photo frame, just single story. And then we are saying it has been displaced initially. Okay, our structure has been displaced initially. Maybe we applied a load slightly here. So we had the initial displacement. So there is this damping, the to and fro motion, to and fro, to and fro. We want to see the damping in this structure. We want to see, maybe we want to analyze at what time with our motion, with our structure. Maybe after an earthquake, you are analyzing that structure to see how long will it take for this structure to stop vibrating, or what will be the maximum response, maximum displacement. Because if it's too much below the limit and the material that you have used is concrete, then there is a deformation or the deflection that it cannot take. So our purpose for this course analysis, structural dynamic analysis, is about to understand how can we estimate damping structures and how can we do the now dynamic analysis in this structure. Or when we use the softwares, what do they do? What is that is running in the background in those softwares, right? So we have now a typical damped motion here. And this typical damped motion, we are showing the initial displacement is equal to 0, okay? So in this case, the motion was not caused by, because it's free vibration, the motion was not caused by displacement, it was caused by maybe just a push. And because of that push, there is the initial velocity. So because if you find this gradient here, if you calculate the gradient, change in u over change in t, you're going to get there that the initial velocity u naught, which is equals to v naught, is not equals to 0. Okay, so we are seeing the first displacement amplitude u1, then you have u2, continue decreasing u3, and we are seeing this exponential decay is given here of our amplitudes, and of course we can see the damping, the peak occurs first at a quarter of the damping period. At a half, we have the first half cycle, and until we have the full period here at the full cycle. Okay. No, not there, not here, here. Sorry, here. Because as you can see, the motion starts here. So this is where we have the full cycle. Okay, the wavelength. So we define something we call the logarithmic decrement because we have seen our amplitude declines in a logarithmic manner. So this is defined as the natural log of u1 over u2, the natural log of the change in amplitude. And of course, the maximum value occurs when the cosine factor, I said when the value of the cosine at the tangent, the point here, will be equals to 1. I mean, it's just from this equation, the maximum value of equation that 7 is when this component here is equals to 1. Okay, this component is equals to 1. So that's just a statement that is made in that line. All right, so we have defined another terminology here, logarithmic decrement. And I believe we have defined enough because already we know our response. Response is how the deformation is occurring with the time. We can be able to define the period of that motion. We can be able to define and express the damped frequency. So our motion is complete. So at any one time, using our expression and we develop this curve, we can be able to know what is the amplitude or what is the displacement and at what time maybe the motion will come to a stop. Now you're saying from equation that 7, this is, want to see it. This is the compact form of our expression, of our solution or our response. From equation that 7, we're saying the expression for the two peaks, of course, we have U1 at T1. So it's like this U1 and U2, we want to express it using now our equation, our expression, equation that 7. Yeah. What is U1? What is U2? We already have defined expressed what is U1 and U2 in equation that 7. So U1, of course, is CE raised to power negative xi omega T1, and U2 will be, the T will be after time TD. And therefore, equation 41, now you just U1, you substitute U1 with this, and the U2 with this. Our equation becomes as shown. So we are trying to get a compact form again of the damping, logarithmic decrement. And that's given by equation 42. And we are saying of course, you can substitute what is TD. And we are saying for small value of damping ratio, of course, if the damping ratio here is very small, it means, of course, 1 minus something very small will be the square root of 1, which is 1. So it means we can use the expression without considering the denominator. Okay, but this just for you to take note of that. So we have seen our logarithmic decrement can be expressed in terms of the damping ratio, and the damping ratio can further be simplified. So why are we doing all this simplification? Because when you are given a certain problem, there are always the values that are given, the known values. So you need to have an expression relating one another so that you can see, based on what I'm given, which is the most suited equation that I can use to estimate or to approximate the quantity that is to be determined, whether it's the logarithmic decrement, whether it's the damping ratio, whether it's a critical damping coefficient, and so on and so forth. Okay. Well, so far up to that point, I believe it should be very clear. As I stated earlier on in the previous lesson, is that deriving is easy. Deriving is tasking, but application is very easy. And why I don't like going direct to just having a question to solve is that when you are deriving, you understand the concept. The eternal is in you. Remember, education is what remains in you after you have forgotten what was done in class for passing. So once you understand this, after you come out of class, you will not be doing maybe this calculation, but the software shall be doing it for them. But you will not just be a blind person. When you do the calculation or you're doing a dynamic analysis, the earthquake analysis and design, you know what is happening behind. Through those derivations, you get immersed. So that's why we do this derivation without just giving you the equation. I could just have come and say that the equation for logarithmic decrement is like this, and this is how we solve it. But I don't find that method to be very good for remembering or for developing. You know, you are instilling knowledge. We are instilling knowledge in you. We are developing your skills and also your problem-solving capabilities. So as you can see, the problem that we have here is a very simple one. And today I'm assuming that people are very, very okay. Oh, yeah, because I issued the note earlier, maybe some of you have gone through them. Yeah, I can't see any question in the chat. So I'm assuming that people are okay, and I'm happy for that. So if you have any query, don't hesitate to put it there so that we can look at it later on. So in this case, a simple problem, we're just saying there is a system, a weight of 50 Newton at a spring of stiffness. So this weight is suspended by a spring. So there is a spring, and then there is a weight there of 50 Newtons. And the stiffness of this spring is equal to 4 Newtons per millimeter. And it's viscously damped. Why you see this word viscously is for it to allow us to assume that the damping force is directly proportional to the velocity. And this is the assumption we made when we are deriving the fundamental equation of motion. Okay, so don't ask why we are talking about that case. Okay, so we are saying there is that, there is our body there, 50 Newton, and then there is a K. And we are given the ratio of two consecutive amplitude. So because it's damped, we know the motion will be like that. So we know this is the second amplitude. We know the first amplitude will be higher or greater than the second because the motion is being damped. So you ask to determine what is the logarithmic decrement. Okay, you know the logarithmic decrement is natural log of U1 over U2. You are given the ratio between U1 and U2. So it's very simple. The second one is to determine the damping ratio, the Xi. Now you look at what is given. That's why I'm saying you have to look at if you have a different relation, because we express this die in different ways. We talked of it being as C over C critical. But here we are not given damping coefficients. So that's why we had to express it in another form so that at issues or scenarios like this, you can be able to come and choose the appropriate expression. So just move quickly with this. We know from equation 44, this is given by damping, logarithmic decrement over 2 pi. And you get it like that. Again, when you're doing your solution in science and mathematics, always be careful about the signs. If it is, there are those which are dimensionless, there are those with the units. You have to be careful. And to know that we are considering with the units is to ensure when you are working, you have expressed it in the same units. Same units. And if there are multiples like kilograms, kilograms and grams, you need to make them to be this consider maybe to grams or in kilograms. Otherwise, you end up having the correct value, but the decimal points are placed in different locations. So now the third one is the damping coefficient. C. The damping coefficient, you just need to refresh and know the different ways that we can express the value C. And then with this, we are using equation 30. We have the damping ratio. We have determined it in part B. K is given. A mass, you can obtain the mass from the weight. Of course, W is equals to mg. And note that we are talking of Newton and millimeters. Okay, so whatever the unit that you are given, that's why you are seeing the G, you're talking of it in terms of 98 tenths times 10, because it's 9.81. And the unit, so that they can rhyme with Newton, millimeters, if we are in the grams, and so on and so forth. And then we end up having what is the damping coefficient, Newton second per millimeter. The last one is what is the damped natural frequency. The damped natural frequency, omega d, you said is omega, the root of 1 minus xi squared. And this is very simple, you just need to substitute that. And as you can see from the calculated values, the undamped and damped frequency, they are very close to one another because the damping ratio was small. It was the damping coefficient, not ratio, the damping coefficient was 0.026. So if you express in percentage, that's just 2.6 damping. So that's why you find they are very close with that. Okay, so you can see the application is very, very simple. How about the second part? I mean, not the second example here, which we are calling example 4, because I number them from the first one from this course. You are given a platform weighing 18 kilograms, supported by 4 columns, clamped to the foundation. So when you hear the word clamped, so you know the head fixity. This helps you to understand the head fixity. Even if you're not given the sketch, now you know how is this column supported at the foundation. So it's clamped, so it's fixed. Because you know it helps you to determine the equivalent stiffness or the column stiffness. So from the experiment, it has been known that a static force applied horizontally to the platform produces a displacement of 2.5. Note that this is static analysis, static force. So from experiment, a static force of 5 kilonewtons was applied. So this is not dynamic force. So we are still in free vibration. So this is just from another experiment of the same platform. It showed this, okay? And if you are talking of static analysis, we have F, we have displacement. So you can already start to imagine what we want to do. We know at static analysis, F is equals to K times delta. So our displacement is 2.5. F is equals to 5 kilonewton. We can get the stiffness. Now it's estimated that the damping in the structure is of the order 5% of critical damping. Okay, so the damping ratio. So you are required to determine the undamped natural frequency, damping coefficient, logarithmic decrement, and how many cycles and time do we need to reduce our motion from 2.5 millimeters to 0.25 millimeter. Okay. So again, it's an easy one because it's just application. So we come here and damped natural frequency. This one we already know. It's omega. It's K over M, and the M is equals to W over G. So you just need to substitute that. So this is why we needed the K, and the K was determined from the force. The static force and static displacement helped us to obtain the K. And then we obtained the omega to be 33.02 Last per second. As you are practicing this, you can punch your calculator so that you confirm these values. I work them on my side. Sometimes you might be tired. And this one again, we did it last year. Is this a new example? I don't think so. Okay, damping coefficient, just take the equation. C is equals to 2, xi root of K over M. Everything is known here, just substitute that. So what is very, you need to be cautious here, I repeat again, is the issue of consistency in the unit. In the way you express your K's and F's and all that, so that you can have consistent unit here. Again, logarithmic decrement. So in this case, we are assuming that the damping ratio is too small because it's 5%, 0.05. But you can even use the equation without, you can try it out. You can try it out because we say the logarithmic decrement is equals to 2 pi xi over the root of 1 minus xi squared. You can use this, or you can even try using this to see whether you get a value which is very different from this. Because we are saying 0.05, then you square that, is something very small. So anyway, I would advise you to be using this expression because you may start asking, how do we judge when the damping ratio is small? How do we know whether 5 is small enough? Okay, so you can be using this expression instead of this. Finally, the last part is on, we want to know our motion is like this. Okay, our motion is getting damped. From an initial value of 2.5, our motion is coming like this. Okay, so we do not know how many cycles that we need to attain so that we can come from the initial displacement of 2.5 or initial amplitude of 2.5 to a case, maybe it could be the third cycle, it could be the fourth cycle of 0.25, okay? But what we know is that there shall be a number of cycles. Let's call them N. And we know the ratio between all of these. If there are 10 cycles, we know U naught over UN will be U naught over U1. This is what we call the dot product. I don't know which unit you started about the dot product and the cross product, whether it was in geometry or algebra. So the dot product, and also in the chain rule, I think you used these, the chain rules in the calculus, so that you could express u naught over un to be u naught over u1 dot, u1 over u2 dot, u2, u3, like that, un minus 1 over un. Okay, so you have utilized that expression. So you take the natural logs, because that's the one that will give us the logarithmic decrement, u naught over un. So if you take the natural log, the dot product of this is the same as summation of the value that we're going to get. So either of these will give us the delta. Okay. So if there was 9 cycles, we'll have 9 deltas. Now the natural log of, we know the starting one is 2.5 of a un 0.25. This will be equals to, sorry, somebody is calling me here. Okay. So if you take the natural log of all that, we are saying this delta, where is it? We calculated it in the, I was lost by that call. We had calculated the delta, the logarithmic decrement to be 0.314. Yeah, so we just substitute this to be 0.314 n. And basically now you are saying n is equal to 7.33. Of course, we don't have a cycle, a fraction. So you say 8 cycles. So for us to reduce our motion, it means for our motion to reduce, from 0.25 to, from 2.5 to 0.25, it means we are going to have 8 cycles. Okay, this is what we are talking about. So the first cycle starts here, ends here. That's one cycle. The second cycle from 1 here to here, second cycle, like so on and so forth. And what is the time for these 8 cycles? Remember, we are talking of the damping period, TD. So we'll have 8 TDs. And we know TD is equals to 2 pi over omega d. Omega d is equals to the omega, the root of 1 minus di squared. So, and we already calculated what was the undamped frequency. So you can see it takes about 1.52. So we are saying until the 8th cycle, if the 8th cycle is here, so you're saying the time that you take that is 1.52 seconds. So you can see very little time. This kind of case of the earthquake. It moves very fast. The many vibrations in a very short time. Okay. And that's the flat. You can see our lesson was easy. It's becoming easy with you having the notes, I believe. You can see Manuel Mangera, you are saying nice lecture. Okay, I hope you're following. But don't be fooled by this simplified work that I have done for you. So until the time that you sit down and work them out, yeah, that's when now will transfer what I have here to your system, yeah, in your mind. So don't just look at this equation and then, even when you are solving, have a book, work them out again. Even if you know the answer, work them out again. Because if you just work out on the handout, and then you are saying, oh, this one I can understand, it have not gotten into your system. You might think that you have gotten it, but if you have this problem and then it comes in an exam setup, and then some small changes are done, you are lost. Okay. All right. And I believe that's enough for today. I have given you an example for working for your practice. And before you even go to the solution, because the solution is given in the form of a tutorial, work it out fast, because it's a very simple problem. And this is a problem that we gave in last year's continuous assessment, a very simple one. And I provided a tutorial in this video. So you can click either of this, or you don't have this link. This I just added later on. Remember, you are not the one that I gave you. These were for last year. Some of them were prepared in 2016. So there are some additional materials that I add. Like if it's this morning, I get some new material, some new book, I can add something. So that's why I say it's always good and important and mandatory to attend the class. Okay. And that's why I was saying it beats logic to give the attendance list. And then I find people 130 logging, and here I'm having it 7. So that's why sometimes I'll not be giving it out. I'll be taking the attendance from this platform from time to time. All right. So just go and find a video that have got this thumbnail. You just see this photo, then that's a video that you have solved that problem. But I'm saying before you go there, work it out. Okay. All right. There are more examples in the book that I have given you. I shared the main reference textbook with your class rep. And it's a very good book, and the latest one, 2019. We obtained it. We were given free access during the time of COVID. But I believe now, if you try to search it, you have to buy it. So they gave us a link and for us to download. So you can use that book without any fear, but don't share it in the internet, because again, that was not the purpose of the others. Just use it, share with your friend. You can read as much as possible. So in that book, there are a number of examples, very good ones that you can use and which are good for you. So that brings me to the end of my lecture for today. I believe so far, so good. If any one of you have got a question, you can ask. In the chat section, I can see we don't have any question. Next session, we're going to look at when there is forcing. But at this stage, I would like to stop there. And welcome. Let me stop sharing this so that I can welcome any question, live question, if there's any one of you with a live question. If there's any one of you with a live question, I want to share the link. If you want to speak, I share the Zoom link here. If not, you can just leave the question on the chat box and we are going to address that. So the class rep, I have shared that. Then I'll answer the question. But until that's the end of today, for today's lecture. So make sure you practice as early as possible, so that you get used to working this out. So I can see, thank you, John, thank you, Kahura. All right, it's a good team. It's a good team. All right, so I'll stop there. We'll meet next week. But if you have any question, you can leave it in the comment after the video, or in any of the videos, just leave it there and then I'll be answering it. All right. Thank you. Bye-bye.